Hello everyone, and welcome to episode 25 of Games with Go. And let me update the title real quick, because it still says 24. So someone in chat is asking about the draw function, which is currently iterating across all the tiles in the level and not just the ones on the screen. Is this a problem? Yes, it's a little bit of a problem. SDL is just going to toss out any coordinates you try to draw that don't exist, but it's a little bit wasteful that we're doing it. So that's definitely something eventually we'll address. We'll want to break out of the loop once we're outside the range of the screen. It may actually not be much difference in efficiency, because SDL is just going to do nothing with it, but it will be a little bit more efficient. And I like to be efficient. Let's get this title updated. Okay, so today we're going to try to add A-star search to our RPG, and we'll be able to use that for at least two things. One of those will be so that we can allow people to use a mouse or touchscreen to click on a position and have the character go there via the shortest possible path. And the other thing we could use it for is for monsters or NPCs, so they can navigate these levels themselves. The monsters, for instance, might see or hear the player and then head straight towards them the fastest way they can. And so A-star search is pretty much the fastest way to do that kind of pathfinding whenever you have a graph. And it may not seem like we have a graph because we have a grid, but a grid is just a graph shaped like so. And so the basis behind all of the kind of graph pathfinding algorithms, sort of the thing we start with, is the idea of breadth first search. So if the player were, for instance, right here, and we wanted to do some kind of pathfinding algorithm with him, the first thing we need to do is a breadth first search. And basically what that means is just starting at that player position and working outward from the player until we've searched the entire graph. So you would, it's a recursive algorithm, so or it's recursive logically, you don't have to implement it that way. But you start at the player and you visit all of the player's immediate neighbors, all the nodes that player is connected to. So on a grid, that's going to be left, right, up, and down, or possibly diagonally if you want to let your grid work that way. So first you'd visit all of his neighbors, or her neighbors. And then the recursive part of it is that for each neighbor you have visited, you also visit all of that neighbor's neighbors. So from here, you would visit this neighbor and that neighbor. And then from here, this neighbor you've already visited, so you're going to skip it, so you'll need to keep track of that. And then visit this neighbor. And then from here, you'll visit this neighbor. You've already visited this one, skip it. And this one, they've both been visited, skip it. So at that point, you've done a breadth first search and visited all of the nodes. So that's sort of how everything starts. That by itself is useful for some things, but by itself is not an A-star search. But that's what we're going to start with. And then what we're going to do is, because whenever you're working on a complicated algorithm like this, and A-star is pretty complicated, you're going to make mistakes. There's going to be bugs, possibly ongoing bugs, where later down the road you think you have it working, but you change a game mechanic, and then your monsters aren't traveling the paths you expected. And it can be really hard to figure out why, if the only way you can debug it is maybe printing out things to the screen or looking at a debugger. So since games already have a visual representation of the world, it can be easy and extremely useful to put some kind of debugging overlay on your game itself so that you can see exactly what your algorithm's doing. So we're going to do that to help us get this done. And it'll probably be useful for other things we're going to do too when we're trying to see how our logic is working to be able to do that. So to get things ready for us, one thing we're going to do is we're going to go into our game, and we have a lot of places where we're using X and Y, and we're going to turn that into a struct, a position struct, just because it'll be easier to work with it. We're going to be putting positions, X and Y positions, inside of maps and arrays and queues and stuff, and it'll be easier to work with if we make a struct out of it. And so for now, the only thing an entity is going to have is a position struct, which makes this seem redundant, but eventually we'll probably have other things and entities as well. So we'll leave it like this for now. Okay, so then anywhere we're using X and Y, we'll now need to change. Let's see. Anywhere we're talking about player. Okay, that won't have to change because we just used an embedding of the position, so that's okay. That's wonderful. Okay, so we've got a position struct with X and Y. And the other thing we want to do is on our level, we're going to add a map. I think we talked about maps a little bit last time. A map is something that associates a key, and you can make the key whatever type you like, with a value, which you can make, again, whatever type we like. So for now, we're just going to make a debug map, which will map positions, XY positions, to Booleans, true or false. And then what we can do with that is in our UI, when we're drawing the level, where's our draw function? Okay, so this is our draw function where we're drawing all the tiles. And we're getting our source rectangles and destination rectangles. And what we can do is we can say if the debug map contains the position that we're going to look at. Let's make that position struct. So position will equal a game.position xy. So we'll see, does that map contain the position we're about to draw? And if so, there is a handy SDL function called setColorMod. And what setColorMod does is that while this is set, any calls you make to copy, while it's copying one texture to the renderer, it's also going to multiply the color you set here on top of it. So by putting a little bit of red here, this is R, G, and B, red, green, and blue, it will basically make the next, all the subsequent calls to render.copy a little bit more red. So it's a way to like color the tiles that we've put in this level.debug map. So what we're going to be able to do is see how our breadth first search is progressing through the level, because we're going to color them red. And then after we're done making that copy, or I guess we can do it like this. We can say else and so if you give it white, basically there will be no longer any change to the texture. So this will make anything we put on in the level.debug map, any XY positions, tiles, it'll make them show up with some red on them so we can see them. So that will be really useful. So now we're going to start breadth first search. We will call that BFS, common acronym for it. And that's going to need copy of the game UI, because we're going to use the game UI to kind of draw what's happening so we can see it. It's going to need the level, and it's going to need a start position, because we're going to start doing a breadth first search from where the player is. So the first thing we need for breadth first search is a queue. And if you're not familiar with stacks and queues, stacks and queues are very common data structures. People use them all the time. So a stack is something where you can put, both of these have operations put and pop. Not all libraries and languages use that terminology, but they will always have something equivalent. So when you put something on a stack, let's say you put in the numbers 1, then you put in 2, then you put in 3. When you pop from a stack, you get them off. You can think of it as you push them down and you get them off the top. So if you pushed 1, then 2, then 3, when you pop, you'll get 3 off the top, and then you'll get 2, and then you'll get 1. With a queue, Q-U-E-U-E, strangest spelling in the world. If you push a 1, and then push a 2, and then push a 3, when you pop, you get the 1. Is that right? Yeah, first in, first out. So stacks are what people call them first in, last out. Queues are first in, first out. You'll see that terminology a lot. So when you pop, you'll pop from the bottom of a queue. So it's basically like standing in line. If you're the first person in line in a queue, you're the first person to get out. That's why they call it queuing in England. And with a stack, the first person into the stack will be the last person out when you start popping. So what we need for this is a queue, not a stack. So Golang does not have a queue built in, but you can make one with a slice. It's not perfectly efficient, but it's pretty good, and it's pretty easy. There are some third-party queue collections you can use, but they use interface. You put void interfaces in them, which means you lose type safety, and you have to cast things when you get them out. So we're not going to use that, and we don't want to have third-party dependencies when we don't need them anyway. So we're just going to use a slice, which is just a growable array. We're going to call it frontier. This will be like the edge that we're searching. And this syntax here, I don't know if I've used this on stream before. This tells you how big to make the slice when you start. And this tells you how much, this is optional, it tells you how much space to reserve. So I'm going to go ahead and reserve 8 slots in the slice, because we're always going to have at least 4 pretty much. And this saves you making unnecessary allocations. You don't have to grow from 1 to 2 and 2 to 4. You can just start out at 8. That can be an easy way to improve performance if you know that your slice is going to get to a certain size eventually. Okay, then we're going to go ahead and put the start position in the frontier. Okay, we're putting that into the queue just by appending. And then we're going to make a map. And this would be a map of positions to bools, which just happens to be the same as our debug map, same types. And we'll go ahead and put our start in there. And we've already visited start, we're on it. And we're going to set level.debug equal to visited. So they're pointing to the same map structure, not separate copies. So while the frontier has anything in it at all, just check the length compared to 0. We get the current position that we're at, which in this case, the first time through will be the start position. And this syntax here shrinks the queue. It says get the slice of the frontier starting at element 1, right? And slices start at 0, so this will be the second element to the end. So we get a new slice that starts from the second element to the end of the frontier. So the first time through here, frontier will be empty. It'll be size 0 for now. Okay, then we're going to loop through all of the neighbors of the current node in the graph, or the current tile of the grid that we're on. We don't have a get neighbors function, so let's write one. And so this is pretty simple. We're just going to return a slice of the positions that are adjacent to the one we're getting. Just call that position. So we're going to return a slice of positions that are neighbors. Chat asks what we're working on today. We are working on A-star search, and we're starting with breadth first search as a basis to get used to what we're doing here, and we're going to visualize it so that monsters can attack us faster. All right, so let's go ahead and make a slice. And basically we're just going to do left, right, up, and down. So we're going to say left is x minus 1, and right x plus 1, y minus 1, y plus 1. And if you want to allow diagonal movement in your dungeon, you can do that too, but I'm not. Okay, so what we can do is say neighbors equals append neighbors right, left, up, down. So now we've got all our neighbors, and we can return. So now we do have a get neighbors function. Let's see, why aren't we happy? I misspelled neighbors. Okay, so now that we have a get neighbors, we need to check first. So we're going to get each node that are neighbors of the current node, as called next. And then we're going to check to see if it's visited already. Because if we've already visited the node, we don't want to visit it again. So we say if not visited, then do some stuff. So we're going to add any nodes that are not already visited to the frontier by appending it to our queue. And then we will mark next as true in our visited maps. We don't visit it again. And then we're going to go ahead and draw the level, because every time we update the visited map, we're also updating the levels debug map. So this will let us see what's happening as it happens. And then we'll do a little sleep. We'll sleep for 100 milliseconds, which will give us time to see how this thing's actually working. All right. So let's add a new input for our player. We'll call it search for now. This will be temporary. And then we'll just say if we hit S, we're going to do a search. Okay, so if the player hits S, we're going to run breadth first search. So let's go to handle input, do case search, And then we will do BFS with the UI, the level, and player.position. And we don't have UI in here, so let's pass it in. And then we'll need to pass the UI in to handle input. All right, let's see what we get. Okay, I'm going to hit S. And we see the breadth first search expanding. And we see a problem in that it is expanding into the walls, through the doors, and so on. So what we need to do is check the type of tile we're hitting and have it stop if it's one that we shouldn't be searching through. So let's add that logic. All right, here we go. So we can basically reuse our can walk function from before. We can say this will check to see if a XY can be walked on. And let's change this to a position to match everything else. That'll be position.y x. Need to make all of these positions. All right, so now all we need to do is check if can walk to the right, then add it. If can walk to the left, then add it. Can walk up, add it. And it can walk down at it. So let's give that a try. All right, so now we see the breadth first search fills up the room we're in. And if we open some doors, start over, we'll see it expand all the way through the level as far as it can. Okay, so that's a good start. But for now, all that's doing is just visiting all of the nodes that are reachable from the player. That's a good start, but now we want to have A* search to actually find the fastest path from point A to point B. So yes, chat says this breadth first search could be a good way to have a bleeding feature. You could fill up entire rooms, or perhaps flooding. You could have flood traps. Okay, let's make a new function. A*. Take in a game UI again for debugging purposes. Now we'll try to get this working tonight, but it's going to be hard, so we might not finish, but we'll get a good start. Okay, so the first step is A star needs a special kind of queue called a priority queue. And the idea behind a priority queue is each thing you put in, so we're going to put positions in, also needs a priority, which is just a number. We'll use an integer to indicate if it should be the next thing out of the queue. So basically, when you push something into the queue, some position and priority combination, when you pop, instead of getting the first thing you put in, you get the thing with the highest priority out. So you can think of it as a queue that you're constantly sorting. And that's how we're going to implement it at first. Go has no built-in priority queue. Most languages don't. And so we're going to have to make one. And eventually we're going to make a proper priority queue, which are usually implemented with a tree, a binary tree with some special properties. That's the efficient way to do it. For now, we're just going to use a regular queue like we have been, and we're going to keep sorting it every time we go through, which will give us the same functionality. It'll let us get it working. It's just slow. So we're going to get it working first, and then next episode we'll make it fast by implementing a priority queue from scratch. Okay, so we're going to need some stuff here. We're going to need sort. We're going to need math if we don't have it already. I think that's all we need. And then we're going to need to make a priority position type, and we're going to need to satisfy a sort interface for it. So we're going to make a priority position struct, which will have a position and a priority. And then we're going to make a priority array type, which is just an array of priority positions. And we're going to satisfy the sort interface for it. So if you do not remember or weren't here for when we did sorting, Go has a built-in sort mechanism. And the way it works is whatever type you want to sort in an array, you have to, or it doesn't even have to be in an array. Whatever you want to sort, you have to provide the following three functions: length, swap, and less, for that type that you want to sort. And then Go has a very efficient sorting algorithm that can sort it for you. So all you have to do is provide these three things for your type. So I'm actually going to copy the example as a basis, because we're only going to be a little bit different. So instead of by age, this will be our priority array. So these are receiver types. So these are functions that will be associated with our array of priority positions. And then the Go sort algorithm will know that and be able to use these functions to do the sorting. So length, you just return the length of whatever collection your thing is. So we can just use length of P, because it's just a slice, and length will tell us the length. Swap is how you change the positions of two indexes, I and J. So this is just identical, we just aren't using the letter A. And then less tells you if I is less, if the item at index I is less than the item at index J. So again, this pretty much stays the same, except we look at priority, not age, like the example was. PE priority. Okay, and that's all you have to do to make a collection sortable. Just provide these three functions, and then the sort interface is satisfied. So back down to A star. So we're going to make a priority queue. We're going to make a crappy priority queue for now. So it's going to be a slice, but this time a slice of priority positions. Remember, we made a type def. Priority array means priority positions, a slice of priority positions. Then we're going to append a priority position. We're going to create one from our start position and give it a priority of 1 for now. And something to keep in mind is A star is something that can handle, let's see if I can undo all the way back to my graph. Yeah. It can handle finding the shortest path on a node that has weights on it. So, you know, say traveling from here to here was really expensive. Like maybe there was slime on the path and this was a really slow way to go. And that these were faster. These had a weight of 2. A star can handle this and figure out that it should go here and then here instead of straight across, because 2 plus 2 is less than 10. And for now, everything's going to be weight 1 for us, so we're going to ignore that aspect. But it'll be ready for us to deal with that if we add this kind of mechanic to our game. Okay, so now we're also going to keep a map of where we came from. So for every node we visit, we're going to record where we came from to get there. And that's going to map one position to another. And so what is going on there, this is sort of the heart of how this works. If this is our start and we visit this node, then the came from for this node is going to point back to where it came from. And then if we later visit this node from here, the came from is going to point back to that node. So if this was our goal, the way you get your path from the player to the goal is you follow the came from nodes. You follow this pointer. Okay, this points to here, and then this points to here. So then you have a list of that node, and that node. And if you play that list in reverse, you get the path from your start to your position. So that's the basic idea of what we're doing. So our came from is going to be a map that keeps track of that. And the start didn't come from anywhere. We're just going to say that it came from start for now. And then we're going to keep track of cost. And like I said before, for now, this is always just going to, like the cost to go from one node to another is always going to be 1, but in the future, we'll be ready to handle varying costs. Okay, and the cost so far start out as 0. All right, so again, we're going to loop while length of frontier is greater than 0. As long as there's still things in our priority queue, we'll keep going. And we'll say current equals frontier of 0. Oh, first, we're going to sort. So to sort, we use the sort package and call the sort function and pass it our thing. Interesting. Sort's not guaranteed to be stable. I think we need stable sort. Is there a stable sort? I think there is. To the internet. Yeah, it's just called stable. So I've explained this on a previous stream, but a stable sort guarantees that if 2 items in the collection have the same value, stable sort will keep them in the same place relative to each other. Whereas an unstable sort will not. It will sacrifice that in exchange for a little bit better performance. So we will sort the frontier, which will sort it by the priority. So that gives us our priority queue. And this, let's make a note here. That this is a temporary solution. Okay. Then we get our current node from the beginning of it. And we can check to see if current I think we need to check the current, yeah. If the current dot position equals the goal, then that means we found our path. Like we're done at that point. So we can stop. Probably will be returning eventually, but for now we'll just say we're going to stop. Okay. Otherwise, we need to shrink our frontier down because we popped the thing off the we popped the highest priority off already. And then we'll loop all over all the neighbors just like before. And then we're going to get our new cost. And this will just always be 1 for now. And then we need to check to see if cost so far already contains next. And because cost so far is a map that does not just contain a Boolean, in order to see if something exists, you can use this syntax. Like this will give you the thing, and this second item in the tuple will tell you if it's there or not. All we want to know is if it's there, so we use underscore to say we don't care about that. So we say exists, and then we can say if it does not exist, or the new cost is less than cost so far of next. And it's important to check this first, otherwise you'll get a bogus value or null pointer exception if you try to get something out of a map that's not there. So this failing will break out of the loop. Or succeeding will break out of the loop, being true. So cost so far, get the new cost. And then we need to get a estimate of what the cost will be from the goal to next. And I think what we can do for that for now is to get the Manhattan distance, which is just you count like how many nodes you have to go in a straight line. But on a grid, you can't actually go in a straight line. Like if you want to get from here to here, you've got to go up, then over, then up, then over. So that is the Manhattan distance. So we'll just do that. Get the X and Y distance. And we'll say that our priority we'll add the Manhattan distance to our cost. And then we'll stick a new priority position onto the queue. And we have to update came from. So that that node knows where it came from. Then we can so if we're going to draw, though, we need to update the levels debug map. And so we'll say we'll make a new map out of it. And then anytime we set came from, we'll also set the debug map so that we can see it. Okay, then our ultimate goal here is to get a path from start to goal. And we're going to want to do that in here once we find the goal. So one thing we can do is we can say p is equal to current.position. And while p is not equal to the start, because remember we're going to be working backwards, right? We have our came from map, which tells us for any node that we've visited where it came from, right? That came from there, that came from there. So we can work backwards from the goal back to the start. So we're gonna want to say, let's just print line this now to see if it looks like it's working. Probably won't be yet. So the current position is going to be at the goal. So we're going to print that, and then we're going to set it equal to where it came from, and print that until we get back to the start, hopefully. And then we'll break out of the loop. And we'll just okay, what's this unhappy about? Should be game UI. Okay, so there's no compiler errors, so it should definitely work, right? Probably not. We'll see. So this is now going to be a star, and we need to give it a position to go to. Let's actually see what position should we try to get to. Let's just try to get, you know, over a couple and up one as a simple test. Then we'll do two level dot player dot y plus one. So we'll try to get to a point 2 to the right and down 1. All right, so we'll hit S, see what happens. Okay, so did we find it? 5 3 5 3 5 3. That's no good. But it does look like it stopped at the right point. Like it was searching and then it hit the goal, so that's promising. It didn't paint the goal red because we broke out of the loop before we got there. Like we could change this to be let's move that up there and see what happens. Still breaking out before we see it. Oh, that makes sense because it's not drawing it. So we should expect it to draw Oh, I'm expecting it to be too far to the right. That's what's wrong. It's just 2 over. Yeah, so it's working right. So this is the goal. And that's getting colored in, and they were quitting. So that makes sense. Okay, so Y is... Oh, I'm printing current instead of P. That's why. Okay, so this is saying 5, 3, 5, 2, 4, 2. So if we go backwards, we should start where the player is. So 0, 1, 2, I guess 0 is here. Zero, 1, 2, 0, 1, 2, 3. What was that 4? Where do we start the player at? 0, 1, 2, 3. I wonder if that's a sign of a bug. But the path does make sense, assuming this is 4, 2. Then we go 5, 2. Well, no, it doesn't make sense. No, he's not scrolling over. Or maybe not printing the last step. Oh yeah, we're not printing the final step. So we need to do one more P. Because once P is equal to start, we break out of this loop and we're not printing anymore. Okay, there we go. So 0, 1, 2, 3, 0, 1, 2. So he starts at 3, 2. He goes to 4, 2. He goes to 5, 2. He goes to 5, 3. Okay, so it looks like we're finding a path. That is promising. So let's actually color the path instead of the searching process. Let's try that. So that would be just replacing these print lines with setting our debug map. It's actually really easy to do this, which is cool. All right, so it's showing us the path in reverse, which is what we expect. All right, that's really cool. Let's try a more complicated one to be sure it's working. So let's say we wanted to make the goal, well, we can just use that same goal, but we'll move. We'll move somewhere where it's not immediately obvious what the correct path is. Oh, that won't work because the goal is relative to the player. What did we say? We'll just make the goal goal 3, 2. Let's open this door too. Make the algorithm work. All right. Look at that. That's pretty cool. All right, so we've got an A* search. And keep in mind, even though we are doing a slow implementation with our constantly sorting the queue, it's not actually that slow. That's just us delaying on purpose so we can see it. If we take that out, I believe it will be basically instantaneous. Yeah. Basically instantaneous. And we could just leave the slow implementation, but I think it will be a good educational stream to learn how to do a priority queue. They're a little bit tricky, but it's not too bad. It's just a tree. We've done trees before. Okay, so this is a good start. What we need to do is, we've got 8 minutes, we can probably do it, is this should actually return, a path. So a array of positions. And we're going to need to reverse it. So can you quickly reverse a slice and go? Does Stack Overflow have a... You can use sort.reverse, but that's kind of goofy. I'm not going to do that. Let's see, how can we do this? Do we know how big it is before we start? We don't. Yeah, we'll just do it. We'll just do it in place. So what we'll do is we'll get a slice ready. We'll say path be an array of positions, and start it out, nothing in it, and then we will append p to the path. Keep drawing it for now, just for fun. P equals P. And then we need to reverse it. So what we can do, so basically we're going to iterate I and j basically in reverse order and start swapping elements. So we'll say path of I, path of j equals path of j, and the path of I. So I is going to start at 0, j is going to start at the length of the path minus 1, so the end. We go as long as I is less than j. So once the two meet in the middle, we'll stop. We keep adding 1 to I and subtracting 1 from j. And we swap as we go. So that should reverse for us. And then we can test that by, let's just move our drawing into there. Let's get rid of the drawing there. And then we'll say for range of path, and let's draw it with a delay so we can see that it's in the right order. Time.sleep. I don't trust that that's all going to work. Okay, if we get here, we didn't find a path, so we'll return nil. Let's see. That worked. That is in the correct order. Thumbs up. Okay, I think that's going to be it for tonight. We've got a working A-star search. What we'll do next stream is use a real priority queue, so this will perform better. So we won't. Oh, one more thing before we go tonight. I added this just before I started the stream. In your input loop, in your get input in the UI, put a little delay. I did 10 milliseconds. You could do 5 or 20. That way, you're not just eating your CPU waiting for key inputs. So it was getting noisy on my machine, and it's wasteful. So put a delay in there. And yeah, we will do a priority queue next episode. Next episode will either be Thursday or next Tuesday. I will not be here Sunday. Might not be here Thursday. We'll see. I'll update on Twitter as soon as I know. Any questions before we go tonight? Questions or comments about this episode or previous ones? Anything you like? And remember, if you subscribe on Twitch, you can use Amazon Prime to subscribe for free. You get access to the source code, or you can donate. If you go to the homepage, gameswithgo.org, you can donate and you'll get source code access. Smashing SF asks if it will make sense to put the UI on its own thread at some point. Possibly. Being a 2D like turn-based game, it probably won't ever be that useful to do that. But who knows? Like if someone imagined some really complicated AI they wanted to do with the game logic, and they wanted the UI to do some fancy stuff at the same time, then it might make sense. And there could be some things that would be easier if you put it in a separate thread. Like for instance, at some point, even while you're waiting for input and the game's not doing anything, you might want to have animations happening or something. And that might be easier to do if we put the UI in a separate thread and communicate with channels. So possibly. And what's kind of neat about if you communicate with channels from the UI to the game, it's kind of equivalent to doing a client-server application. So it's sort of doing the same thing you would need to do if you were networked, which we're almost doing already. So it would be easy to do that. It's not a bad idea. I'll hang on for another couple minutes in case there's any more questions or comments. Let's try a trickier search. And it went that way because that door is closed. So one enhancement we could add to this, maybe we can do it next episode when we do the priority queue, is doors really shouldn't count as impassable. It should just count as a more expensive movement because you have the opening step. So if that were the case, this would probably have picked this direction, because one extra step to open that door wouldn't be slower. Chat asks if we're going to be working on an inventory system at all. Yes, I'm sure at some point we will do that. I have no concrete plans yet, but I do have some ideas. I'd like to have maybe a little bit of like crafting in the game where you could mix and match potions or spells or something to solve problems. I'm thinking about maybe having the ability to make levels with puzzles in them that you can solve, as well as just hacking at monsters. So we'll see. All right, thank you everyone. Good night for now. See you again soon.